So to work with our own processor, what you need to do is you need to go to Ortus and you need to download this MCU in Logisim for exercises and MCU documentation. It should be available in Ortus in this subject, and you scroll down and here it is. Download this file and this MCU documentation Excel file. And you should be good to go. So let's see, I click here. Okay, something strange. I'll check out what's going on there. So do I need to edit? So I set it to force download. So when you click on it, it should just force download now. So now you go to this file, you click on it, and for example, in this Chrome, it says that, you know, do you want to download it? I'll say, download this file, and it should appear someplace here. Okay, here it is. And this MCU documentation also appears. Since I had these files, they appeared with a new name, but generally you should just download the files that are here. And if you successfully downloaded them, then you should open them using Logisim. So you go to Logisim, File, Open, go to Downloads folder, MCU, and here it is. So this all project. Okay. If you successfully downloaded the file and opened it inside Logisim using Open Logisim and then File, Open, and then select the file, write in the chat box that you did it. And also, if you downloaded this MCU documentation Excel and you open it, and it opens some table named instruction set, then also write in the chat box that you successfully opened the files, just to make sure that there's no problem with that. Okay, so it's possible to download and to open. So in Ortus, at the very bottom, MCU programming 1980s style. So we will do programming the way that first people did programming in 1980s and in 1970s. Okay, so computers were these big houses with blocks of relays built in the way that we built them in Logisim, and people had to program them. But wait, they didn't have computers and beautiful graphical user interfaces to write the code. So basically, the first people wrote the first codes by hand on paper based on the documentation of the processor. So this is what we will do today. So let's check out. So in our, basically this processor that we have in Logisim, you will finish building it during the labs, but we have kind of advanced in our lectures further ahead than the lab. So let's just imagine that we have completed building our microcontroller. So this is our microcontroller. And if you really look at its contents, so it has this 1-bit adder, 4-bit ripple adder. This version also has this carry look ahead unit, 8-bit adder, and or XOR not, and so on. These blocks, these first I don't know how many 100 blocks, are used just to build arithmetic logic unit. And as we talked previously, so the arithmetic logic unit, you give two numbers, select operation, and it calculates the result. The next block after arithmetic logic unit is general purpose registers. So processor has to have some temporary storage of numbers. General purpose registers, in our case, we have 8 of them. Each is 8 bits long. And to do some manipulations, you need to get first the numbers inside the registers, and then you can add them or subtract or shift bits inside the registers through arithmetic logic unit, and so on. The next part is this instruction decoder. I think we spoke about it last time. So basically it takes the instruction and it just forwards corresponding bits to the control signals of the processor. And it looks a little bit more complicated, but in the labs, as you build them, you'll realize that it's actually really simple. There's a finite number of signals, and you just have to configure them properly for each of these small in number instructions. And so the CPU itself only consists of arithmetic logic unit, general purpose register where the numbers are stored, instruction decoder, and here the instruction goes in. It's temporarily uh, saved in instruction register, so it doesn't wiggle around during some processing in the processor. It's forwarded to instruction decoder. Decoder forwards the bits of the instruction to their corresponding places in CPU. So some bits are received by GPR, some by arithmetic logic unit. Here you have multiplexers that are also controlled. Um, this multiplexer, for example, selects what number to write into general purpose register. A number from random access memory, a number from flash memory, a number from arithmetic logic unit result, or status register. You can also read status register. Here is data in from random access memory and data out to random access memory, so we can write and read from RAM. Source for data out is always general purpose register content, and data in goes into registers, and so on. And you have this program counter. When you reset the processor, it jumps to 0, so all programs start at address 0. That's the convention. And every time you do instruction, it automatically increments and moves ahead one instruction. So nothing really that much. So, and here's the difference between microcontroller and the processor. So basically the difference between MCU and CPU is that microcontroller consists of CPU and also program memory and random access memory. So in desktop computers, CPU is a separate chip, program memory is a separate hard drive, and random access memory is separate random access memory slots. You can upgrade them if you want to. Uh, and correct to be said, actually program memory is also part of RAM because desktop computers are Neumann architecture where you don't know how much flash and RAM you need, so they are in the same space. But microcontrollers just differ from computers that it's all built on a single chip. You buy a microcontroller, it has some small flash, some small RAM, and some small processor. So it's just built in. Okay, so now enough of that. Let's start to program our processor. So to do some programming in our processor, we need this instruction set documentation. And it basically says it names all the instructions that we can do on this processor. So today we will look at only 6 instructions, and there will be something like 5 advanced instructions, but generally 6 instructions for today. So what can we do with our processor? And we will do it a little bit different order than in this document, because it's built the way we build the processor, but we will program it in the kind of opposite direction. So, and we will check out, we will sniff what the assembly programming language is and what it means. So we will write a little bit in assembly. Have you ever written a code in assembly programming language? Type in the chat box yes or no. In the chat box, you can write if you have ever programmed anything in assembly programming language. Somebody says no. Okay, so then I will introduce you to the assembly programming language. You know, some basic concepts. So assembly programming language is a programming language where you write the instructions of processor, and these instructions are exactly the instructions that processor can perform. Okay, so we have documentation which names the few instructions that processor can do. RISC processors can have, for example, only 25 different instructions, and that's it, nothing else. And in assembly language, you write these instructions exactly how the CPU will perform them. And assembly language generally has the following structure. So first, it's written like this. First word that you write or don't write is label. And label actually translates to the line number. So ideally, we would want to write assembly language code in a text editor, which shows the line numbers. But the problem is that most text editors only show line numbers starting from 1, but in programming, everything starts from 0. So we would need such environment where it shows a line number starting from 0. And I'm not sure if Notepad++ offers that. So we will just write in Notepad. You know, it's not going to be that complicated. But generally, you use a text editor where you can write starting from 0, line 0. So first is a label, then you use a tab to organize it beautifully, tab. Then next thing that you write in your instruction line is instruction. And then you press tab. And the next thing that you write after instruction is operands. It's in plural. So operands are the objects on which you perform the instruction. For example, you want to add two numbers, the instruction is add, and operands would be the registers that you want to add together. And some instructions, for example, have only one operand. For example, increment instruction, it only needs one number. And there are some instructions that don't need any operands. For example, all processors have operation called NOP, and NOP is no operation. It's sometimes used just to slow down the processor, for example. Just don't do anything for one clock cycle. So operands can also not be given at all. And the final column is comment, and in assembly programming language, comments start with a semicolon. This is why C programming language, in C programming language, all commands end with semicolon. It comes from assembly programming language. I don't know why, but this is the way how it's written. And using this knowledge, And I will actually put a label in simple braces, because label is not used if it's not necessary. So it's just not written at all. But this one tab is used uh, to write the instruction. Okay, so let's see. Um, let's just write a simple assembly code and check out, how it's being constructed and how it's being executed in the CPU. You will also have to do this. So I'll do something and then I'll ask you to also do something. So first thing that we want to, for example, do is first to do anything with some numbers in processor, we need to get those numbers inside the CPU. Okay. So how to get numbers inside CPU? Getting numbers inside CPU means copying them into some register and assigning a value to a register is done using instruction called LDI. It's called LDI, load immediate. In assembly programming language, and historically, immediate means um, a number, a constant number, k, So let's say what we want to do, I'll just write it as a comment. So I'll start with semicolon. Let's say we want to assign value. I want to say that, for example, register R1 is equal to, for example, number 55. Okay. How do I do that? I do it with LDI instruction. I load number 55 into register R1, for example. So let's do it. In assembly language, it would be written as LDI, then tab, then which register, register R1, then comma, and the second operand is number 55. Most assemblers that I know support 3 or even 4 ways to write a number. First way is just you write a number as decimal. The second way to do it is to write it as hexadecimal number. So decimal 55, hexadecimal 37. You could also write 0x37, or you can also write 37H. Most assemblers also understand this as a hexadecimal number. Then in some old platforms, if you start a number with 0, it will be assumed to be base 8, or uh, I don't remember its name. Hexadecimal, octal. I think it's octal counting system where the base is 8. We can actually convert it base 8 octal number. So base 8 to decimal. Enter octal. I needed the other way around. Swap. Decimal number is 55. Octal number is 67. So if I wrote 067, it would assume that since it's starting with 0, it's an octal number, base 8. For some really old 3-bit processors, it would be used. And also many assemblers, for example, Arduino AVR assembler accepts binary numbers written in the following form: 0B, and then binary number with bits. So for example, decimal 55 is in binary 00110111. Okay, so this is also accepted, but this notation was removed and not used in C programming language. So C programming language only accepts this decimal number, hexadecimal, second way of writing hexadecimal, and I think that C programming language also accepts octal numbers. but not these binary numbers. So unfortunately, in C programming language, you cannot write bits as they are, but in assembly language, all versions that I know allow this. But this is what I need to also tell you. Unfortunately, assembly programming language is not really standardized, and each manufacturer that produces processors invents its own assembly language, its own notations. For example, in some assembly languages, if you write a constant number, you need to put hashtag in front of it. Okay, so number 55. That's how they do it, you know. And something like at in front of it means that it's address and so on. So you would need to check out the documentation. But in our case, and I think it's also in Arduino and also in ARM, GNU, GCC, it's just number, it's just written as is, no symbols in front of it. So I'll write them in decimal so that it's easier to understand. So this line LDI R1 55 means basically R1 equals to 55, okay? Now, how do we tell the CPU that we want to load number 55 to register R1? And here's a very simple thing. It was historically done by hand. Each assembly instruction directly translates into a single machine code or operation code or just single entry of flash memory. And this is why assembly process is actually a simple translation process done by a translator. So when you write code in C programming language, it's compiled from C to the corresponding assembly language. And if you use different CPU, different manufacturer CPU, different architecture, compiling process will differ. But assembly process is just basic translation. Check this out. LDI, for example, in our processor, LDI instruction, if we look at the documentation right here, it says LDI in machine code is first 4 bits have value 0, 0, 1, 0. So in our flash memory, we can immediately write 0, 0, 1, 0, and it will tell the CPU that this instruction is load immediate. And instruction decoder will do all the switching accordingly in the CPU. Next 4 bits tell the register into which we want to write the number. So we want to write the number into register R1. So I just write number 1 in binary in 4 bits. So I would write 1, but since it has to be a 4-bit number, I just add 3 zeros in front. So this 4-bit number is 1, which says register R1. It selects the register. And final 8 bits are the number that we want to write into the destination register. So number 55 in binary is 0, 0, 1, 1, 0, 1, 1, 1. So if I give my CPU this string of ones and zeros, it will perform this operation, okay? And we will check it out, but in Logisim, I cannot write binary numbers. Logisim accepts hexadecimal numbers. So I need to translate this, just calculate it in hexadecimal and then write it to the program memory. So 0, 0, 1, 0, you're programmers, so you probably can do it in your head, but I'll do it in programmers calculator. 0, 0, 1, 0 is in hexadecimal number 2. 2. Next is 0, 0, 0, 1 is just 1. 0, 0, 1, 1 is 3. And 0, 1, 1, 1 is 7. So, and if you really look at this instruction in our simple processor, translating from assembly to machine code is really simple because first 4 bits tell the instruction. So 0010 is LDI. Next 4 bits tell the register R1, so this number is just 1. In hexadecimal and in binary, the same, we have only 8 registers. So this will be number from 0 to 7. And then number 55, well, if I write in decimal 55, it says hexadecimal is 37, so I can just write 37 right here. Final 8 bits is the number, so this is the instruction. This is the instruction in machine code in hexadecimal format. So if I take this 2137 and I type it using hand tool into the program memory, 2137, and then I reset the processor and do 1 clock tick, rising edge, falling edge, and I go into CPU in GPR and I check out, then I see that register R1 contains value 55. This is exactly what the processor did. Let's do it again. Maybe you didn't believe me. So I reset the processor. What does it mean to reset the processor? It means resetting program counter to 0, so that this is how reset button automatically resets the program to the beginning. It just resets the program counter to 0. And by convention, in practically all processors that I know, also reset signal resets all registers in general purpose register block to 0. So they're all 0. 0, 0, 0, 0, 0, 0, 0, 0. Now, if I go to MCU and I perform the first instruction using rising edge reads the instruction and falling edge writes the results into registers or RAM or whatever, I go into CPU, I go into registers, and I see that in register R1, number 37 was written, or 55 in decimal. So I guess that I did everything correctly. So this is how we write assembly instruction. We translate it by hand to machine code, and then we write this machine code in binary in a perfor board or by hand in this logisim, and the processor knows what to do. If you understood it, write in the chat box that you understood all of this rank that I just told you. If you didn't understand, you can maybe write a question in the chat box. Okay, so I give you, like, I don't know, a moment to write in the chat box if you understood everything or not really. Okay, happy to see that it's clear for at least 2 people. Okay, let's hold you accountable. And now you need to do yourselves the second thing that we want to do. Let's say that I want to set register R, I don't know, for example, R0 equal to some number, for example, 102, or maybe 103 will be something like this. Okay, so register R0 equal to 103. How can we do it? So if we want register R0 to be equal to 103, then we need to do instruction LDI R0 103. Then we need to translate it one-on-one to assembly. Then we need to, in machine code, then we need to write this machine code in hexadecimal numbers, and then we type it into our program memory, we execute it, and we check if it's correct. So now you do on your own yourselves the second instruction R0 equal to 103. Okay, try to do it yourselves and try to run it on the CPU as the second instruction. I will do it silently in my notepad in my screen, but you can try to do it on your own in your computers and try to run it on your CPUs. This is why I asked you to download this MCU and this documentation. So I'll try to do it, and you also try to do it, and then you can compare if your results are the same as mine. So first thing is to write this in assembly language. So how do we set R0 equal to 103? It's LDI R0 103. Next, we translate it to machine code. LDI means the first 4 bits are 0, 0, 1, 0. Register R0 is just 0. 103 decimal 103 is 0. Okay, so when you finish and you check out and it works, you can write in the chat that you did it, so that I know that you've done it, and then we can discuss the result and move forward. That is fantastic. Okay, so one person successfully did it. Let's just discuss it. So how do we, what instruction can copy a constant number into a register? It's LDI instruction. So I just write LDI, then destination register R0, 103, load 103 into register R0. And to translate it to machine code, in our case, it's really, really straightforward. Instruction translates to this first 4 bits. Then next 4 bits is the register number, and next 8 bits is just the number. And actually, you can also write it in hexadecimal if you think about it. LDI is 2. It's also 2 in hexadecimal numbers. Register 0 is 0 in hex. And number 103 is 67 in a hexadecimal. So basically, is created really simply. And if you would check out, for example, Atmel instruction set, AVR instruction set summary, blah, 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 manual. It's done in this processor almost the same way, just the bit locations are a little bit different. Here you can see, oh, look, program data addressing modes, blah, blah, blah. Here's the instruction. And in their case, destination register is located in the last 4 bits. And this is why there's no universal assembly programming language, because each manufacturer puts the control bits of the registers in different locations, right? So, and also AVR processors have 32 registers. This is why this number is actually 5 bits. But inside the instruction, destination register is last 5 bits. In our case, it's second 4 bits. Here again, 2 registers. Register 0, bit 0 to 4 is destination, 5 to 9 is source, and then there's operation code, and so on, right? So I'm not lying to you. I'm not imagining these things and coming up with them at random. It's the principle is how it's done in all processors from past probably to future, or at least near future. Okay, so we have translated our second instruction. Okay, so let's say we want to add these. Oops, I had another lesson before this, so my voice is a little bit old now. So next instruction that we want to do is we want to calculate the sum of these two numbers, but we want to preserve the numbers. We don't want to overwrite any of them. So we want to, for example, calculate that R3, okay, R2 is equal to R1 plus R0. How can we do that? So if you didn't sleep through previous lessons, you know that these cheap, simple microcontrollers only work on 2 registers. And the first register that we write is the one into which the result will be overwritten. So if we would write add R1, R0, it would put result into R1 and overwrite its original contents. And that's not what we want to do. So if you want to add 2 registers and save the result in the third register, then you need to do 2 operations. First, you need to copy one of the numbers into result register and then add the second number to the result register. It is called, partially it's also called accumulation principle. Okay, so one of the registers accumulates the result. So actually, to add 2 numbers into the third number, we need to do 2 separate instructions. And first of them is, for example, copy register R1 into R2. Copy one number into result and then add the second number into the result. So first thing that we need to do is copy register R1 into R2. Copying value from one register to the second in most assembly languages is called mov, from move. In some other assembly languages, I think in Texas Instruments it's called copy, CPY, but I think that in ARM and in most other languages it's called mov. So move. First register is the register into which the result will be written, so it's going to be R2. And the second is the source register from which to copy, so it's R1, for example. So as a comment, I write R2 equal R1. Now we need to translate this into machine code. And for arithmetic logic units, it's going to be a little bit different. So all arithmetic logic unit instructions will start with zeros because these instructions are absolutely identical, except that we switch between arithmetic logic units operation selector. But everything else from the CPU standpoint is the same. You take 2 registers, you do something in arithmetic logic unit and write the result back into registers. So the beginning of all of these instructions will be the same. It's going to be 0, 0, 0, 0. So because it's arithmetic logic units sub instruction mov, which is right here, first 8 bits, first 4 bits will be 0, 0, 0, 0 because it's arithmetic logic unit instruction. Next bits are destination register. So first is this, then it's destination register. Destination register is register R2, so it's 0, 0, 1, 0. If you know from your head, this is binary 2. Next 4 bits is operation selector, which is hardwired to arithmetic logic units operation selector, this input. Okay, so there's no magic. So mov instruction is instruction number 7. In our processor, is just for simplicity, it's realized through arithmetic logic unit. So instruction number 7 is 0, 1, 1, 1. And the second argument operand is register R1, so it's number 1, 0, 0, 0, 1. So these bits will select first register, which is the destination register, and the last 4 bits select the second register, which is the source register from which to take information. The middle here is operation, and here is that it's arithmetic logic unit instruction. And now let's write it in hex 0x. Actually, you can do it in your head. 0, 0, 0 is 0, 0, 0, 1, 0 is 2. In hexadecimal, 0, 1, 1, 1, 1 is 7, and 0, 0, 0, 1 is 1. So, you know, it's simple to translate. And I'll just write it in the next field in program memory. So 0, 2, 7, 1. If I use hand tool and click on it, it has a red box around it, and I can write in the value, and then it's also selected by program counter because, you know, we write it and then we write it and then we do the clock. So if I do clock, before I do it, I can check out that register R2 is empty, is 0. I do clock one time, rising edge to read instruction and falling edge to execute it. I go into CPU, into GPR, and I see that register R2 contents changed from 0 to 37. Basically, it copied R1 through arithmetic logic unit into register R2. Okay, so, and the next part, to add these numbers R2 equals R1 plus R0, we need to do the add instruction and add to the register R2 to the resulting register, register R0. Okay, and to do that, to translate it into machine code, again, it's arithmetic logic unit in sub instruction add. So first 4 bits is 0. Second 4 bits are the destination register, register R2. So it's 0, 0, 1, 0. Next is operation. Add is operation number 0. So it's 0, 0, 0, 0, because we have, it's a 16-bit number. Sorry, 4-bit number, 16 combination. And then source register is register R0. So it's 0, 0, 0, 0. So in hexadecimal, if you really think about it, it translates really simply 0, 2, 0, 0 is addition. So in this, I write 0, 2, 0, 0. I do clock rising edge. It reads the instruction falling edge. It executes instruction, jumps to the next one. And I go into GPR and I see that register R2 contains value 103 plus 55 is 158. It contains 158. So I go to calculator. I can do it 103 plus 55 is 158, which in hexadecimal is 9E. So it shows that basically everything works correctly. Okay, so these are arithmetic logic unit instructions, and so that you can try to do something on your own, let's do it the following way. You need to increment register number 3. So what you have to do now, I give you a task to calculate R3 plus plus in C programming language. You know, because this plus plus thing is really, really popular in programming, all microcontrollers support it as a direct instruction. You don't have to load one into one register and then add it to the second register. CPU, arithmetic logic unit, as we built it, supports increment instruction. So now you need to write on your own and translate into machine code instruction int increment. And here's the thing, I'll just tell it to you. So increment works only with destination register. It takes the destination register, adds one, and writes into the destination register. So source register is not used by increment, decrement, negate, also not used by not, also not used by logical shift, left, right, and rotate. So final 4 bits are don't care bits. You can add any value to them, all ones or all zeros, they'll just not be used. They'll be discarded by instruction decoder. So you actually only need to care about first 3 nibbles, and the final one is, for example, all zeros. Okay, so now on your own, try to write a machine code in hexadecimal format that adds 1 to register R3. So initially, after reset, since we haven't done anything to register R3, its content is 0, 0. Let's say you want to increment it. So now you need to write an instruction that increments register R3. I will shut up and I'll write it on the computer silently, and you try to write it on your computer without looking and try to do it in the processor and see if it works or not. Okay, somebody wrote something. The result for add for me is minus 98. So the reason that your result was minus 98 is as unsigned number. If we imagine that it's 8-bit positive number, it's going to be 158. But if we imagine that it is a signed number, then as in 2's complement form, this is the same as minus 98. So in my Logisim, I went to File Preferences. I checked out this layout, and here I select first radix when wire poked is unsigned decimal, and second radix is signed decimal. I set it this way, so when I click on a wire, the first number that it says is as unsigned number, because most of the time people who program microcontrollers actually, I think most numbers that we use are unsigned. We want to use all 8 bits without sign, because most of the cases the counters are positive. Analog to digital converter results are most of the time single-ended positive. So we don't really need to use signed numbers. So most of the cases it's just we use all 8 bits as unsigned number. We just make sure that we never go over 255. But if we wanted to use signed numbers, well, then 158 cannot be written in 8 bits. We can write only from minus 128 to plus 127. This number is greater than 127, so it wouldn't fit in 8 bits, so it wouldn't be a correct number in 2's complement format in 8 bits. This is why you were seeing minus 98. Okay, so did you successfully write increment instruction in machine code? Okay, so first 4 bits say it's arithmetic logic unit instruction. Next 4 is register number 3. Next increment is the second one, counting from 0. And the final bits is don't care. If you wrote all ones, it would calculate the same way. Doesn't matter. So it's 0, 0, 0, 0, for example. So if you wanted to build the most energy efficient processor in the world, then you would want to set the last bits which are not used equal to the last bits in previous instruction, so that the bits don't change and you don't have to flip some field effect transistors to opposite values, because processor consumes electricity only on signal changes. If the signal is constant, almost no electricity is used. But only when you flip bits, it's when you need energy. You need to recharge the field effect transistors to opposite values. So for example, if we wrote 2, 0, these bits wouldn't have to be changed. So you would save electricity. But of course, nobody really does that. That would be really complicated. So, okay. So we can load numbers, we can do some arithmetic logic instructions on them. What else? Since processors only have few registers, in reality, all variables that you define in your C programming language code are actually stored in random access memory. You know, you can have, for example, an array of 1000 numbers. Of course, they don't fit in CPU. They will all be written in random access memory. So for this reason, we have instructions called load from RAM, and either they're called LDR, as in this case, or they're called sometimes simply LD, like load, and store to RAM. Copy register value into RAM is either ST or STS or STR. They have different names. And in our simple processor, we have just one way to do it. We have, for example, this store instruction, which says store register value in some specific address. So in programming language, when you define variables, for example, unsigned integer x, right? The compiler actually assigns a numeric value to x, its location in RAM. You know, like if you understand, if you know anything about pointers, then x actually is like a constant pointer to memory location where its contents are stored. So, and the compiler usually doesn't do any trickery. If you define a variable, it reserves one space in RAM, as many bytes as you selected. So, for example, in our case, the correct way would be to say unsigned integer 8 bits x. It looks at the RAM. It says, okay, in RAM address number 0, I don't have anything. So a compiler assigns RAM address 0 for x, right? So when you write, for example, x equal to 55, What actually happens in, I don't know, any C-like language, what actually happens is first, number 55 is loaded into some temporary register. So in our case, for example, we did it actually LDI, R1, for example, 55. And the second thing that happens is this register R1 contents are written into the address that is assigned by a compiler to hold X value. So for example, since we didn't have any variables defined previously, then we will just assume that X location is register number 0. So if I write X equals 55, then it means store to RAM contents of register R1 into address number 0x00. Okay, because microcontrollers are, to be cheap, they have to be made really simple. This is why there isn't such instruction that could take a number from program memory and put it directly into random access memory. It would need so many select signals for address selection, RAM, and so on, that processors would be very big and complicated. Intel processors, desktop machine processors, of course, they could do it because they are more expensive. They cost 300, 500 euros. So yeah, okay, they can do it so that the processor works faster. But microprocessors, microcontrollers that cost something like 2 euros or maybe 50 cents, of course, they don't have that much wires inside. So in CPUs, in microcontrollers, you can only load a number into register and then store the register contents into the random access memory location where your variable is reserved. So this is actually how it happens. So if I write, for example, unsigned integer 8-bit x equals to 55, then let's just reuse the code that we had here. 55 is loaded into register R1 and its contents are written to RAM address of X, so 00. So let's do the second part, the first part we have. So we want to do the store register R1 contents into a random access memory location 0x00. So translating this into machine code will be actually also really simple. So store instruction is 0100. So I write 0100. Next 4 bits is the register. So register R1 is 001 in 4 bits. And then the address, 8 bits. So in our case, we have only 16-byte RAM, but our processor can support up to 256 bytes because we have 8 bits to select address. I selected this to be 16 bytes so that all bytes are in the same view. If we had more bytes, they would be hidden. So to have them all visible, we have RAM with 16 locations. So let's check out 01000001. So address is 0, so it's just 8 zeros. And in hexadecimal is 0x. 1000 is 4. So it's 4. Register R1 is just 1, and address 00 is 00. So if I write in my flash memory 4100 and I do clock rising edge, you can see that the instruction has selected random access memory byte 0 and set it into write mode. And I do the following edge, and the number 37, which is 55, is written into random access memory location number 0. Okay, so this instruction basically tells instruction decoder to connect register number R1 to random access memory address 0. If I click on address, it says 0. If I click on data, it says 55 because it's connected through multiplexer directly to RAM. And instruction decoder just sets it into writing mode and enables clock. And during the following edge of the clock, the value was written into RAM. Okay, so now your job is, for example, to store the value of register R0 into random access memory address number 1. So let's say in C programming language, we would have unsigned 8-bit integer y equal to 103. And how would it happen in assembly language? Actually inside the CPU. So first, the compiler reserves mem address 0x01 for y, and then it loads 103 into some register. For example, we wrote it into register R0, and then it writes the contents of R0 into RAM address number 1. So now you need to write, to translate into assembly, basically store register R0 contents into 0x01. Can you do it on your own? I'll do it silently. You try to do it yourselves, and you can check out if you do the next clock cycle, will it write into this next random access memory address the value. And if you accidentally hit the clock more times, you can always reset. Reset means jump back to the beginning of the program. Clock needs to be low, it needs to be 0. And then you do the first instruction, second, third, fourth, fifth, sixth, and seventh, I don't remember. Yeah, 4100 was the last that we did, so I reset it again. I go to this, and the next one will be this. So to store register R0 into address 01, store 0100 register R0 address and hex. If you succeeded, write in the chat box that you did it and everything worked. Okay, so we know how to load numbers, we know how to store them. Okay. So reading from random access memory would be just as easy. And the last instruction that we talk about today will be jump instruction. So jump instruction has many uses, but basically it just jumps to a different location in the code. For example, jump to the beginning of the code again. Let's say that we want to build an application that just blinks an LED. So so to blink an LED, in microcontrollers, it's done in the following way. Some RAM locations, some random access locations are also connected bit by bit to microcontroller pins, so that when a certain bit is set high, then the corresponding pin is also set high using a stronger, bigger field effect transistor, right? So writing 1 to a certain random access memory location would set it high, and writing 0 would set it low. So for example, we want to blink an LED, we set it high, then we set it low, and then we jump back to the place where we set it high. Then we set it low, then jump back to the place where we set it high, so it's set high again, then we set it low, and so on. So it's like a loop. It happens, forever while true, and so on, and it just does the same thing over and over again. So that would be a usage for jump. But the classic usage of jump that I will tell you today is how to end the program. You see, if I keep clicking clock, if the clock of the CPU keeps oscillating, then we run into some flash memory territory that we have not initialized. And actually, let's see, for example, edit contents. So from previous year, there is some part of some old program inside of the flash memory. And fun fact for you, since flash memory eventually wears out, programmers and chip makers don't really want to erase and write into flash memory that's not used. So when you write a code, you flash it and it's written into the program memory. If you write a new code, only the part where new code exists is written to new code. And if it's shorter than previous code, then some parts of the old code still stay inside the flash memory at the end of flash memory, because we shouldn't erase the flash memory uselessly. So flash memory will always, I don't know, almost always contain some parts that have some random code from previous functions, from previous programs, or maybe it will just be reset to all zeros. And all zeros is actually an instruction. All zeros is an instruction from arithmetic logic unit. Add register R0 to register R0. So if we would continue our code, it would start to increase, or I would say double, the contents of register R0. So it would corrupt our data. And that's not desirable. And this is why all programs in the world end with the following line: end, jump, end. And this is the first place where we are using labels. So label is basically the location in flash memory of this instruction. Or since each instruction is one word inside the program memory, it's also the line number starting from 0, counting from 0. So, as an example, so this is instruction number 0, this is instruction number 1, 2, 3, 4, 5, 6, and this is instruction number 7. So, and this label actually is equal to 7 because it's the line number counting from 0. So jump end actually is exactly jump to instruction number 7. And what happens is when we execute this jump to instruction number 7, which is this same instruction, we kind of hang into this line forever. So it says jump to line number 7. It jumps to line number 7. It says jump to line number 7. Okay, it jumps to line number 7. The line number 7 says jump to line number 7. So basically the processor just hangs on this line, and you would think, wow, that seems stupid, but actually it's not. This way, the program counter never executes the next lines, which are, for example, not initialized. So this is how all programs in the world are ended. And even when you write C programming language code, you write your code, but actually compiler silently and secretly puts this instruction in assembly language to the end of your code anyway. Okay? Because if for some reason your program is executed and finished, when it exits your int main function, well, what is it going to do? Is it going to explode, or is it going to burn in flames or something? No, it will just run the same line forever. Okay, so this is how all programs are ended. So we will just translate this into assembly, because I'll give you an example. For example, this flash memory location would be initialized to 0, 0. So if we do the clock, you see that some old code is executed and something weird starts to happen to our code. You see our RAM contents are being overwritten with this old code, which is not erased. We don't want that to happen, so we need to add this end, jump, end function in line in the end, which we will translate. Jump is 0101. Next 4 bits are not used, it's 0000 in our processor, and then absolute address. So address number 7, instruction number 7, basically it says to which instructions counting from 0 to jump to instruction number 7, so it will be 0000000111. So 7 in 8 bits. Our flash memory is 256 bytes in this case. So in hexadecimal is 0x, 0101 is 5, next is 0, 0, and 7. 5007 means jump to line number 7, which says jump to line number 7 forever. So if I write it here, 5007, then let's reset our processor. Let's run the program again, and let's see what happens when we reach this location. So first instruction was load number 37 in hex to register number 1. Next is load number 67 in hex to register number 0. Next instruction was something like copy the value, then add two registers together. It's right here. So add register R2 and R0. Next is increment register number 3. Next is 4100. It's store register number R1 contents into RAM location number 0. We do it 37 is written. Next 4001 is store register number R0 contents to address number 1. So 67 is written. And next is end, jump, end. Let's see what happens when I click this. You would think like nothing happens. What actually happens is on rising edge, this instruction is read into the CPU, and program counter's multiplexer is switched to input number 0, which says instead of adding 1 to program counter, set program counter equal to 7. So program counter says I am 7. 7 plus 1 is 8. But this multiplexer, which is switched by this beginning jump instruction 0101 to position number 0, instead of adding 1 to program counter, it says program counter equal to the bottom 8 bits of the instruction, which is equal to 7. So program counter stays 7 instead of auto incrementing. So this is what the jump instruction does. It switches, it forces a constant into program counter, and this constant is 7, which is the instruction number which says load 7 into program counter. So what happens is load 7 into program counter, and it does it all the time. So it jumps to line number 7 and just doesn't move forward. Okay, so this is how we end the program. Okay, this was a little bit of an intro into assembly programming language. For our use case, if you want, well, actually nobody really writes assembly language code anymore, because C programming compilers are actually so good that C programming compiler and optimizer can actually generate an even more efficient code than if a human writes the code in assembly language. For some time, it wasn't the case. Actually, assembly language was used up to, I think, year 2005 in microcontroller world. Uh, it was really popular, and I know there are some old people who still write code in assembly, but and of course it makes you feel really smart and so on. I can also write an assembly language, so I'm like this cool dude, but unfortunately it's not really efficient anymore. I remember when I started programming microcontrollers in something like year 2005, uh, you know, it was often the case when you write a code in assembly language, you write the code in C programming language, and you see that C programming language code is so much worse. There's no optimization. The registers are used in stupid manner and so on. But the compiler developers have really improved the compilers, and now you don't have to write in assembly anymore, even for microcontrollers. However, assembly language is still taught to programmers at least for one semester, and at least in some non-essential subject, just so that you understand what the CPU actually does when you write some code in C programming language or in high-level programming language. For example, when you write y equals 103, what actually happens inside the CPU? First, compiler reserves place in random access memory for y. It fixes the address. So y is like a constant pointer. And then it loads this 103 into a register from flash memory, and then it stores this value into random access memory. So it takes 2 clocks, and sometimes maybe it has some implications, or you care about it. Okay, so I think if you have some questions, you can ask them. I think that we can finish for today, and next week we will do something more complicated, which will be, we will use branches. So jump jumps to some location in code, to some function or whatever. Branch jumps to a different location only if a certain flag is set or clear. So here are all possible 8 combinations. So if 0 is set or clear, carry bit is set or clear, negative is set or clear, and signed overflow bit is set or clear. So we will do it next time. So for example, we want to do something 5 times. We decrement it until 0 flag is set. If it's set, then we exit the loop, for example. We'll just check out how it's done. So if you have some questions, you can ask. Could you go back on your notes a moment? Do you mean this notepad? And the second question here, pointers are only in RAM or they can be stored in registers? So talking about pointers, in this case, this Y is like a free floating pointer that we need to remember in our heads, right? We just need to remember that address location 0x00 is reserved for our variable number y, and x is 00 and y is 01. But in a CPUs, you can also store this number into a register, and you can do this so-called indirect memory load, where you have instruction. Our simple processor doesn't have it, but basically all processors have it. It would be called something like LD, load into register, for example, R1, value stored in pointer register, for example, register R5. So there would probably be an at symbol in front of it. I think this is how ARM Cortex microcontroller assembly language says it. Basically, it says load into register R1 the value that is stored in RAM address, which is pointed by register R5. So our processor, we can add this functionality. It would just add so many new cables that we didn't want to do it. But generally, yes, you can store a pointer into a register. So for example, beforehand, you write, for example, LDI R5, for example, 1, 0x01. So now R5 has address number 1, and when you write load into register R1 something at register R5 address, it will set R5 on the address line. So it will say 1. Then, and the data in address number 1 will be saved to R1. So yes, the pointers can also be stored in registers, and you can dereference by pointer. This is exactly how it happens in C programming language. Basically, what you're saying is, for example, some A equals to value pointed by B. So B is register R5 and A is register R1. Okay. And most processors have this really cool thing that you can also tell it to auto increment the pointer after this instruction. So register R5 contents go to address line, register R1 is reading from data line, and register R5 is also thrown into arithmetic logic unit increment instruction, and its value will be incremented by 1. So you can, in single instruction, you can do this A equals to value pointed by B plus plus. So processors have this hardware acceleration, and it's made so that you can faster iterate through an array. You don't have to write that R1 is equal to value pointed R5 and then int R5, which is another instruction, another clock cycle. So modern processors like Cortex processors or Intel or AMD, they have this thing that you can tell it to automatically add 1, 2, or 4 to this number, because if you know it, 32-bit numbers take 4 bytes in RAM, so you need to add 4, address needs to jump 4 places forward. Just, so that you know. In 8-bit processors, it's always just add 1. So yeah, our processor just doesn't have this feature because it would be even more cables, even more complicated, but generally, yes. Next question was, could you go back on your notes a moment? Okay, so here's the notepad. Did you have some question about it? I was like blah 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 about something you maybe wanted to ask. Okay, so if you don't have any more questions, we can finish today. And the next week, we will check out the branch instructions, and then you will need to write some more code. For example, you will have to write, actually, it will be like a graded homework. You will have to write an algorithm which multiplies two numbers. So I'm going to write two numbers in RAM, for example, 5, 0, 5, and 4. And you will have to write a program which reads the two numbers into registers and then multiplies them and writes the result into the next register. So 5 times 4 is 20, and I think it's 14 in hexadecimal numbers. So I would want this code, I click clock, and until it says 14 in this memory location. So we will do it next time, and you will have similar homeworks later. So because our processor cannot multiply by arithmetic logic unit, we don't have such instruction. So we will need to write a code, a software in assembly language, which multiplies two numbers. And this is actually how some functions for 8-bit microcontrollers are implemented in C programming language. So when we write A times B, the compiler automatically takes a pre-written assembly code and replaces whatever we wrote with that assembly code. So some assembly is still written in the compiler world to make the compiled code to run faster. Okay, so I guess it's all for today. If no more questions, then we meet. So tomorrow you have a lab. You will do a little bit more in this arithmetic logic unit world. You will build a general purpose register and will connect it. And yeah, and then next week we have a lecture. Okay, so goodbye.